Just to give you a quick introduction of what you're seeing, this is what our telemetry collector is actually getting from the network. So it's Grafana. It's basically an open source dashboard. Some of you might know that. It's getting data from an InfluxDB in the back end. The Juniper telemetry sends to a collector, puts that in the InfluxDB. It has nothing to do with DDoS mitigation yet. It's just to visualize how much traffic is going through our network right now. If you remember the network, I just put it at my topology. We have border routers on the left, we have the core routers in the middle, access routers on the right. We have 3 traffic graphs here. The top traffic graph is actually the interface on the border router, which is connected to the internet. And we have about 50 megs of traffic currently egressing into the internet because we are a content provider. In that specific example, we are serving content. We also have a little bit of traffic, which is next to nothing, which are the requests for these contents coming in to the network, and we are serving about 50 megs. Very few traffic just because it's a fully virtualized network. There are 6 VMs, traffic has to pass multiple times. We just don't want to overload the host, but for demo purposes it's more than enough. The second graph shows the interfaces which are connected to the A10 TPS, so the scrubbing device. Right now there are only rarely some peaks in there because some protocols are being talked there, BGP is running, other protocols are doing their stuff. So currently no live traffic is going through the TPS at all. Down here we have the access layer. It's flipped because from the view of the router, traffic is coming in from the content server into the router, and on the other side of the network it will egress into the internet. So the same traffic should be up here and here. The resolution is about a second, so it's not 100% exact the same spike here as in the same second here, because first of all, traffic has to go through the network, so there are a couple of milliseconds delay in between them, and every router will export the traffic statistics. It's slightly different situations, but the traffic levels should be next to the same. If you would have the same traffic level in a classic SNMP-based, RRD-based solution, you would have a flat line because it would just average out all of the traffic. But here we are actually getting traffic every second, and we are simulating a couple HTTP clients in the background, so actually there is a specific moment in time where no request is coming in, so no traffic is going out, so you could see that's in fact a bit of stuff going on here. If you look into the Flowmon monitoring center, there the evening out comes into play. It's basically more or less a flat line of traffic because flows will be sent out at specific intervals from the routers to the Flowmon. You can tune that down to a couple of seconds between flow intervals, but it will even out at one point. And from that graph alone, it's not very, very interesting what you can see here. The beauty comes if you drill down into your specific traffic things. There's a huge amount of things you could, from your live view, just drill down into. Stuff like source port, destination port, IP addresses, and all of that stuff, which is not that interesting, but on a service provider perspective, you always care which autonomous systems are sending traffic to me, or which autonomous systems are receiving traffic from me. So for example, if you're a content provider, you of course are interested in what are my clients. If you're an access provider, you're interested in where does my content go in order to find out where to invest in terms of peerings or whatever. We can do exactly that. We can filter by source OS. Keep in mind, it's a virtualized environment. So there's not much traffic going on. It's only a bit of simulated traffic. And to no surprise, we are currently simulating mostly Facebook traffic. So 41 gig of our traffic is Facebook traffic in here, and just a little bit of stuff which is not assigned to any autonomous system. Autonomous system 0 is always displayed when it's kind of your own network. So we have clients from my own network which are doing traffic as well. All my transfer networks all my transfer nets in my network, my loopbacks, they're doing a bit of traffic which is exported as well. So that's one of the things you can get from here. If you're interested into what kinds of protocols are being used, you could just drill down into the source port distribution. Just takes a moment to update the statistics then. And most of the traffic is currently being sourced from HTTP, which is no wonder because we are simulating HTTP clients. And most of the rest is just some random higher port because that's the opposite side of the traffic. we are currently generating. So far nothing unusual. What I will just do is I will start an attack. That's an XCR traffic generator. I use that to create stateful traffic, and I use that to create my attack traffic right now. And while the network reacts to that, I will just go over slide deck once again. I've just started an attack. Of course, all of the evil guys wear black masks. That's why the guy on the left side is now sourcing the yellow attack. The yellow attack is hitting the red customer or target on the right side. It might put additional problems for the gray service because the attack is currently moving along these three routers. They might be overloaded. For example, capacities in the backbone might be oversubscribed. The attack might hit wherever. So something is wrong and we need to react to that. What then happens is we have our analyzer detecting the attacks in seconds. It will find out there is an attack, and it will then instruct the network to do the redirection. It will do that by sending BGP routes with a specific next hop to our border routers, which will put it into the appropriate layer 3 VPN, which will then bring the traffic to our TPS. Once the attack traffic reaches our TPS, it will be scrubbed, and only good traffic will be sent back. Due to the fact that we are redirecting destination IP addresses, not only the attack, but also the good traffic will be redirected via the TPS. So the red traffic, which was the original good traffic, will also be redirected, but the TPS is configured in a way that it will not scrub the good traffic. The good traffic will be sent back to the network. So, if we are then coming back to our overview of the network, what happens is, inbound on the border, which is the negative axis over here, we have about 20 Mbits of attack traffic coming in. That's our attack. For a brief period of time, a couple of seconds, it actually was able to reach the target and do whatever harm it was able to do during that period. Then the network reacted. It shifted the traffic over to our TPS. Attack traffic is still coming into our A10 TPS, but it's no longer leaving the A10 TPS. It's just the normal background traffic, so the normal requests basically, which are still going in. And yeah, that's just showing you what happened in the network, and then we will have a quick look in how that relates to our different tools. That's the Flowmon DDoS Defender. What we see is there's an active attack. It's on a specific segment because we are here pretending to be a hoster of Facebook, so we just pretend that Facebook is hosted in our data center. That's why the segment is called Facebook. The attack was detected, a mitigation was started. What actually did happen while the mitigation was started? First of all, it shows you which IP addresses were under attack. So 10 IP addresses were under attack. What did it do? It applied redirection. Applying redirection, there is no more verbose information in here. It just applied your redirection rule you configured otherwise. As I mentioned, it's just an IP announcement with a specific community sent to the network. The network will then put it into the VRF, so that's nothing specific for the Flowmon solution. The dirty VRF solution I'm using here is just one of many ways of integrating stuff into your network. I have a complete presentation on about a dozen ways to integrate these kind of scrubbing devices into existing networks, and believe me, I've done that numerous times for numerous service providers, and no integration is the same between two networks because all of them are slightly different. So attack is mitigated. What's actually going on the A10 during that time? You might have seen that during your lab examples. That's basically, by the way, that's the only physical appliance taking place in this exercise. It's one of the smaller ones, but it's just the only physical appliance we have in our lab. What happened is an incident was created for the attack. And due to us being lazy, the attack is pretty boring and pretty uninteresting. It's just something which is caught by the anomaly detection up here. You can see there's still traffic passing, but there's currently traffic being dropped. Every now and then that number increases. And as you might seen, you can drill down and find out what kind of problem is there. It's TCP, ZUN, and FIN. Actually, we are sending packets with both ZUN and FIN set in the layer. That's traffic you will never see in a real-world network. So the A10 is dropping that right away. And while we're at the A10, I will just quickly show you we have two objects predefined, quite the same UDIT predefined, basically two mitigation zones, and the magic bit which I just talked about is there are no IP prefixes configured manually for that specific segment, but down here there's this magic hook from layer 3 peer. So if there are specific routes being advertised with a specific community, I can't remember where I can find the policy on the web UI, but on the CLI, the policy is bound to the BGP peer and will just select the zone where the traffic has to be redirected in the end. Okay, then when we stop our attack, a couple things will happen. First of all, the attack will stop to actually hit the network. What will not stop immediately is the redirection. So for a specific amount of time, redirect of the clean traffic, remember we also redirected the clean traffic through our mitigation center, is still going through the TPS, which doesn't matter because it's not dropped at the moment. Right now we've tuned the Flowmon solution that it can detect in few seconds that there is actually an attack. If you look down here, it's actually about half a minute until it moved the traffic away, but it takes about 1 to 2 minutes in order to get the traffic back to the normal traffic flow, which is not a problem at all because usually you wouldn't care if the device is still forwarding your traffic. What then will happen in DDoS Defender is this will shortly update. It will shortly update. It will go to a non-active state. After it goes to a non-active state, the mitigation will stop. So it's already not active. In about a minute, it will just stop. Once the attack finishes, you will be able to get additional information about the attack. It will generate information about what the attack was actually doing. You can get that while the attack is running anyway, so you don't have to wait until it's finished. You just do it right now. It generates the file. We'll download the PDF document, and if we open that, you get a bit of information about how many traffic was there. You get a bit of information of what the attack signature was in case you want to reuse that at one point. You get information about the target IP addresses, about the kind of attack which was there, about TCP flags being used in the attack. No wonder SYN and FIN was set in the same packet, so that's a breakdown of what was used there, so you can get that afterwards. Top source countries, it's just simulated prefixes, so it's just one country right now because we only have put one netblock in there, so nothing too exciting about that in this specific example.